somewhere in the constellation of Taurus, roughly 6,500 light-years from Earth, there is a cloud of gas expanding outward into space. It has been expanding for nearly 1,000 years. Chinese astronomers recorded its appearance in the summer of Tain 54, when a new star suddenly became visible in the daytime sky, bright enough to see without instruments, brilliant enough to cast faint shadows at night. For weeks it lingered, then slowly faded from view, leaving behind what centuries later would be called the Crab Nebula. But the nebula is not the most remarkable part of this story. At the center of that expanding cloud, hidden within layers of glowing filaments, lies a small, rapidly spinning object barely 20 kilometers across. It rotates approximately 30 times every second. It contains roughly 1.5 times the mass of our Sun, and it is, by almost any measure, one of the most extreme objects in the observable universe. It is a neutron star. To understand what a neutron star truly is, it helps to begin with a simple question, one that sounds almost too basic to ask, and yet has led physicists into some of the most challenging territory in modern science. The question is this: what happens to matter when you compress it beyond every limit we know? On Earth, matter behaves in familiar ways. Solids hold their shape, liquids flow, gases expand to fill their containers. These are the states of matter most of us encounter in everyday life, governed by the interactions between atoms, between the electrons that surround atomic nuclei, and the electromagnetic forces that hold molecules together. Under ordinary conditions, atoms maintain their structure. Electrons orbit nuclei at defined energy levels. The space between atoms, while small, is real. Matter, in a sense, is mostly empty. But the universe is not always ordinary. In certain environments so extreme that nothing on Earth can replicate them, matter is forced into states that challenge our understanding of physics itself. Temperatures rise beyond billions of degrees. Pressures climb to levels that would crush any material known to engineering. And gravity, the weakest of nature's fundamental forces on human scales, becomes overwhelmingly dominant. These are the conditions that create neutron stars. When a massive star, one with at least 8 times the mass of our Sun, exhausts the nuclear fuel in its core, it faces a crisis that has been building for millions of years. Throughout its life, the star has maintained a delicate equilibrium. The outward pressure generated by nuclear fusion in its core has balanced the inward pull of its own gravity. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. In the most massive stars, this process continues through neon, silicon, and eventually iron. Each stage produces less energy than the last. Each stage lasts a shorter period of time. The final stage, the fusion of silicon into iron, may last only a single day, and then it stops. Iron is the end of the line. Fusing iron does not release energy, it absorbs it. When the core of a massive star fills with iron, the engine that has sustained the star for millions of years simply ceases to function. In that moment, gravity wins. What follows is one of the most violent events in the known universe. The iron core collapses inward at a significant fraction of the speed of light. In less than a second, a region roughly the size of Earth is crushed down to a sphere approximately 20 kilometers in diameter. The outer layers of the star, no longer supported from below, come crashing inward and then rebound outward in a catastrophic explosion. A core collapse supernova. For a brief period, the dying star may outshine an entire galaxy. But at the center of that explosion, something survives. The collapsed core, now composed almost entirely of neutrons, the subatomic particles found in every atomic nucleus, stabilizes against further collapse through a quantum mechanical effect known as neutron degeneracy pressure. It is no longer a star in any traditional sense. It has no nuclear fusion. It produces no new energy from its core. And yet, it is one of the most physically extraordinary objects that nature is capable of creating. This is where our documentary begins. Over the course of this journey, we will move inward layer by careful layer through the structure of a neutron star. We will explore what scientists have discovered about these objects since they were first predicted nearly a century ago, and what questions remain unanswered despite decades of observation and theoretical work. We will examine the crust, where matter forms crystals of neutron-rich nuclei. Unlike anything found elsewhere in the universe, we will descend into the outer core, where neutrons may flow as a quantum superfluid with zero viscosity. And we will reach the inner core, a region so dense, so far beyond the reach of current experiments, that physicists genuinely do not know what state matter takes there. The answer to what lies inside a neutron star is not simply a list of materials or a diagram of layers. It is a story about the limits of human knowledge, about what happens when we push our understanding of nature to the very edge and find that the universe still holds secrets we cannot yet unlock. The night sky appears quiet from where we stand, but within it, scattered among the stars, these extraordinary objects spin in silence, small, dense, ancient, and still not fully understood. Let us begin. The story of neutron stars does not begin with observation. It begins with imagination, the careful, disciplined kind of imagination that theoretical physicists use when they follow the mathematics further than any telescope can see. In 1932, the English physicist James Chadwick confirmed the existence of the neutron, a subatomic particle with no electric charge, sitting alongside protons inside the nucleus of every atom, heavier than hydrogen. The discovery was a landmark moment in nuclear physics. It completed our basic picture of the atomic nucleus and opened entirely new avenues of research into the structure of matter. But within just 2 years, a far more extraordinary idea would emerge, one that most physicists at the time considered little more than a curiosity. In 1934, 2 astronomers working at the Mount Wilson Observatory in California proposed something remarkable. Walter Bade, a German-born astronomer known for his careful observational work, and Fritz Zwicky, a Swiss-born physicist known for his bold and often unconventional ideas, published a brief but astonishing paper. In it, they suggested that when massive stars reach the end of their lives and explode as supernovae, they might leave behind an incredibly dense remnant composed primarily of neutrons. They called this hypothetical object a neutron star. The proposal was extraordinary for its time. Bade and Zwicky were suggesting that an entire star, an object containing more mass than our Sun, could collapse into a body only kilometers across. The densities involved were almost incomprehensible. A single teaspoon of neutron star material, if it could somehow be transported to Earth, would weigh roughly 1 billion tons. The very idea seemed to stretch the boundaries of physical plausibility. And yet, the mathematics supported it. If gravity were strong enough to overcome the electromagnetic forces that normally keep atoms apart, if the electrons surrounding atomic nuclei could be forced inward until they merged with protons, the result would be a sea of neutrons packed together at nuclear density, the same density found inside the nucleus of an atom, but now extending across an object tens of kilometers in diameter. It was a prediction born not from observation, but from the logical consequences of known physics pushed to extreme conditions. For more than 3 decades, neutron stars remained purely theoretical. No telescope could detect an object so small and so distant. A body 20 kilometers across, sitting thousands of light years away, would be far too tiny to resolve with any instrument available in the mid-20th century. Some physicists continued to explore the theoretical properties of these hypothetical objects. Others quietly doubted they existed at all. Without observational evidence, neutron stars occupied an uncertain place in astrophysics, mathematically plausible, physically extraordinary, and entirely unconfirmed. That changed in the summer of 1967 at the Mullard Radio Astronomy Observatory near Cambridge, England. A young graduate student named Jocelyn Bell was helping to operate a newly constructed radio telescope. The instrument had been designed by her doctoral advisor, Anthony Hewish, to study the scintillation of distant radio sources, the twinkling of quasars caused by the solar wind. It was a large but relatively simple array, spread across several acres of English countryside. Bell's task was to analyze the data miles of paper chart recordings that scrolled out of the telescope's receivers every day. In the autumn of that year, Bell noticed something unusual. Among the expected signals and terrestrial interference, there was a small, repeating pulse, a brief burst of radio emission that appeared at remarkably regular intervals. The pulses arrived approximately once every 1.337 seconds. They were precise, they were consistent, and they did not correspond to any known astronomical source. At first, the discovery created more confusion than excitement. A signal this regular, this precise, seemed almost artificial. The research team privately labeled the source LGM1, Little Green Men 1, half-jokingly acknowledging the possibility that the signal might be of intelligent origin. The idea was never taken seriously as a scientific hypothesis, but the nickname reflected the genuine uncertainty surrounding the discovery. Nothing in nature, as far as anyone knew, produced radio pulses with such extraordinary regularity. Within weeks, Bell discovered a second pulsing source in a different part of the sky, then a third, then a fourth. The existence of multiple sources in different directions eliminated any realistic possibility of an artificial origin. Whatever was producing these pulses was a natural phenomenon, and it was not rare. The question became, what kind of object could produce radio pulses with such mechanical precision? Several explanations were proposed. Perhaps these were pulsating white dwarfs, the dense remnants of lower mass stars, oscillating in a way that produced regular radio emission. Perhaps they were orbiting binary systems, with one object periodically eclipsing or interacting with another. Each hypothesis was examined against the observed properties of the signals, their period, their regularity, their energy, their spectral characteristics. The answer came from the theoretical physicist Thomas Gold. In 1968, Gold proposed that the pulsing radio sources were rapidly rotating neutron stars. His reasoning was elegant. A neutron star, he argued, would possess an extremely strong magnetic field, a relic of the original star's magnetic field, compressed and intensified during collapse. This magnetic field would not necessarily be aligned with the neutron star's rotation axis. As the star spun, beams of radio emission generated near the magnetic poles would sweep across space like the beam of a lighthouse. If Earth happened to lie in the path of one of these beams, we would detect a brief pulse of radio energy once per rotation. The model explained nearly every observed property of the signals. The extraordinary regularity of the pulses reflected the stable rotation of a compact, massive object. The short pulse periods, some less than a second, were consistent with the rapid spin expected of a collapsed stellar core. The same way a figure skater spins faster when pulling their arms inward. The high energy of the emissions was consistent with the powerful magnetic fields predicted for neutron stars. And the gradual slowing of the pulse periods over time, which was soon detected, matched the expected energy loss from a rotating magnetic dipole radiating energy into space. These objects became known as pulsars, pulsating radio sources, and their discovery provided the first strong observational evidence that neutron stars were real. The confirmation came remarkably quickly. In 1968, a pulsar was discovered at the center of the Crab Nebula, the same expanding cloud of gas left behind by the supernova recorded by Chinese astronomers in 1054. The Crab pulsar rotated approximately 30 times per second, making it one of the fastest pulsars known at the time. Its location at the center of a confirmed supernova remnant provided a direct, physical link between supernova explosions and the formation of neutron stars, exactly as Bardian's wiki had predicted 34 years earlier. The discovery transformed astrophysics. Neutron stars moved from theoretical curiosity to observed reality. Pulsars became some of the most precisely studied objects in the sky. Their clock-like pulses, used as tools for measuring distances, testing general relativity, detecting gravitational waves, and probing the interstellar medium. Jocelyn Bell's observation remains one of the most important discoveries in the history of astronomy. The Nobel Prize in Physics for the discovery of pulsars was awarded in 1974 to Anthony Hewish and Martin Ryle. Bell herself was not included, a decision that remains widely discussed in the scientific community to this day. But the discovery of pulsars was only the beginning. Confirming that neutron stars existed raised an immediate and far deeper question, one that scientists have been working to answer ever since, and one that remains at the heart of modern astrophysics. We knew neutron stars were real. We knew they were dense, compact, rapidly spinning, and strongly magnetized. We knew they were born in the depths of massive stars, and that they contained roughly 1 to 2 solar masses, compressed into a sphere smaller than most cities on Earth. But what, precisely, were they made of? What happened to matter when it was crushed to such extraordinary densities? What physical states existed inside these objects? What forces held them together? And what happened in their deepest interiors, where pressures and densities exceeded anything that could be studied in even the most powerful particle accelerators on Earth? These were not merely questions of astronomy. They were fundamental questions about the nature of matter itself. Questions that connected the physics of the very large to the physics of the very small, linking gravity, quantum mechanics, and nuclear physics in ways that remain incompletely understood. Answering them would require decades of theoretical work, new generations of telescopes, and eventually, an entirely new way of observing the universe, not through light, but through the vibrations of space-time itself. The journey inward was about to begin. To understand what lies inside a neutron star, it helps to begin at the surface, though even the word surface requires careful qualification when applied to an object this extreme. On Earth, a surface is something we can stand on, touch, or see. It is a boundary between solid ground and open air, between ocean water and atmosphere. We understand surfaces intuitively. They are part of everyday experience. But a neutron star's surface exists under conditions so far removed from anything on Earth that our everyday intuitions become almost entirely useless. Consider the gravity alone on the surface of Earth. The gravitational acceleration. We experience the force that keeps us grounded, that pulls a dropped object downward, is approximately 8 meters per second squared. On the surface of a neutron star, that same quantity is roughly 200 billion times greater. An object dropped from a height of 1 meter above a neutron star's surface would strike it, traveling at roughly 7 million kilometers per hour. A human being standing on such a surface, an impossibility, but a useful thought experiment, would be instantly compressed into a thin film of matter, less than an atom thick. This is the environment we are now entering. The outermost layer of a neutron star, if one exists at all, is an extraordinarily thin atmosphere. Not all neutron stars are believed to possess atmospheres, but those that do may have a gaseous layer only a few centimeters thick, perhaps even less. This atmosphere is composed primarily of hydrogen or helium, possibly with traces of heavier elements, depending on the neutron star's history. In some cases, material falling onto the neutron star from a companion star or from the surrounding interstellar medium may contribute to this thin gaseous envelope. despite its extreme thinness. This atmosphere plays an important role in how we observe neutron stars. The thermal radiation emitted by a neutron star, the X-ray light that allows us to study its surface temperature, passes through this atmosphere before reaching our telescopes. The composition of the atmosphere affects the spectrum of that radiation, subtly altering the pattern of wavelengths we detect. By carefully analyzing these spectra, scientists can attempt to determine what the atmosphere is made of, how hot the surface is, and even estimate the neutron star's radius, a measurement that, as we will see, carries profound implications for understanding the interior. Beneath this vanishingly thin atmosphere lies what scientists refer to as the envelope, a layer perhaps a few meters to a few tens of meters deep, depending on temperature and composition. Here, matter is still composed of recognizable atoms, though the conditions are extraordinary by terrestrial standards. Temperatures may reach millions of degrees. The atoms are fully ionized, stripped entirely of their electrons, creating a dense plasma of bare nuclei and free electrons. The density increases rapidly with depth, rising through values that would already be remarkable by earthly standards, but are still far below what lies beneath. And then we reach the crust. The crust of a neutron star is one of the most unusual structures in the known universe. It is not a crust in the geological sense, not a layer of rock or mineral sitting atop a molten interior. It is a crystalline lattice of atomic nuclei, primarily iron and other heavy elements, arranged in a rigid structure and embedded in a sea of free electrons. The nuclei are packed far more closely together than in any ordinary solid. The electrons move freely between them, much as they do in a terrestrial metal, creating a material that in some ways resembles an extraordinarily dense metallic crystal. At the very top of the crust, where densities are roughly 1,000,000 times greater than the densest materials on Earth, the lattice structure is relatively straightforward. Iron nuclei, the most stable nuclei in nature, sit at regular intervals, locked into position by the electrostatic forces between them and stabilized by the surrounding electron sea. The material is rigid, extraordinarily rigid. The shear modulus of neutron star crust material, a measure of its resistance to deformation, is estimated to be roughly 100 trillion times greater than that of steel. If it were possible to extract a small sample of this material and bring it to Earth, no known force could bend or break it. But as we descend deeper into the crust, something remarkable begins to happen. With increasing depth comes increasing density, and with increasing density comes increasing pressure. The weight of the material above pushes inward with staggering force. At each successive layer, the nuclei are squeezed more tightly together, and as the pressure rises, the nuclei themselves begin to change. Under normal conditions, an iron nucleus contains 26 protons and 30 neutrons. This is its most stable configuration, the arrangement that minimizes nuclear binding energy and makes iron the endpoint of stellar fusion. But under the extreme pressures found deeper in the neutron star crust, this configuration is no longer the most favorable. The surrounding electron sea is compressed to such high densities that a process known as electron capture becomes increasingly common. In electron capture, an electron is forced into a proton, converting it into a neutron and releasing a neutrino. The result is that nuclei at greater depths contain progressively more neutrons relative to protons. These neutron-rich nuclei are exotic by terrestrial standards. They are isotopes that do not exist naturally on Earth, forms of matter so unstable under normal conditions that they would decay almost instantaneously in any laboratory. Yet here, stabilized by the immense pressure of the surrounding material, they persist. The deeper we go, the more neutron-rich the nuclei become. The crust transitions from familiar iron through increasingly exotic isotopes nuclei with 50, 60, 80, even more than 100 neutrons packed around a diminishing number of protons. And then, at a depth of perhaps a kilometer or so below the surface, we encounter a boundary that marks one of the most important transitions inside a neutron star. Scientists call it the neutron drip line. At the neutron drip line, the nuclei have become so overwhelmed with neutrons that they can no longer contain them all. Neutrons begin to leak out to drip free from the nuclei and exist independently in the spaces between them. Below this point, the crust is no longer simply a lattice of nuclei in an electron sea. It becomes a lattice of nuclei immersed in both a sea of electrons and a sea of free neutrons. This free neutron gas fills the spaces between nuclei, and its presence fundamentally changes the physics of the material. The free neutrons that drip out of the nuclei are believed to form a quantum superfluid, a state of matter in which the neutrons flow with zero viscosity, without friction or resistance. Superfluidity is a quantum mechanical phenomenon that has been observed in laboratory settings, was most famously in liquid helium, cooled to temperatures near absolute zero. But inside a neutron star, superfluidity may occur at temperatures of hundreds of millions of degrees, conditions that seem paradoxical until one considers that the relevant energy scales at nuclear density are vastly higher than those of ordinary materials. What counts as cold for neutrons packed at nuclear density is still extraordinarily hot by everyday standards. The existence of a superfluid component inside the crust has observable consequences. Pulsars, the rapidly rotating neutron stars discovered by Jocelyn Bell, gradually slow down over time as they lose rotational energy through electromagnetic radiation. This slowdown is generally smooth and predictable, but occasionally, a pulsar will experience a sudden, tiny increase in rotation speed, a brief spin-up event known as a glitch. These glitches have been observed in dozens of pulsars, and one of the leading explanations involves the superfluid interior. The idea is this: as the rigid crust of the neutron star gradually slows, the superfluid neutrons within it may continue rotating at their original speed, unaffected by the friction that decelerates the crust. Over time, a difference in rotation rate builds between the crust and the superfluid. When this difference reaches a critical threshold, the superfluid may suddenly transfer angular momentum to the crust, causing the abrupt spin-up observed as a glitch. The process then resets, and angular momentum gradually builds again until the next glitch occurs. This interpretation is not universally accepted as the complete explanation for all glitches, and the details remain an active area of research. But the basic framework connects directly observable pulsar behavior timing, irregularities measurable with radio telescopes on Earth, to the quantum mechanical properties of matter deep inside the neutron star crust. It is a remarkable chain of reasoning, linking the rotation of an object thousands of light years away to the behavior of subatomic particles in conditions no laboratory can reproduce. As we continue descending through the crust, the nuclei grow ever larger and more neutron-rich. The lattice structure persists, but the nuclei themselves occupy an increasing fraction of the available space. The free neutron gas between them grows denser, and as we approach the base of the crust, a region where densities reach approximately half of nuclear saturation density, the distinction between individual nuclei and the surrounding neutron gas begins to blur. Here, at the very bottom of the crust, theoretical calculations predict one of the strangest phases of matter anywhere in the universe. As nuclei grow so large and so closely packed that they begin to merge, the material is thought to pass through a series of unusual geometrical configurations. Spherical nuclei may elongate into cylindrical rods. Those rods may flatten into parallel sheets. The sheets may develop cylindrical holes, and eventually, the remaining nuclear material may form isolated spherical bubbles within a continuous sea of neutrons. These phases have been given an informal name that reflects their resemblance to familiar forms. Scientists call them nuclear pasta. The terminology is light-hearted, but the physics is serious. The pasta phases spaghetti, lasagna, bucatini, and other playful designations represent genuine predictions of nuclear theory applied to the extreme densities at the base of the neutron star crust. Whether these phases actually exist, how thick each layer might be, and how they affect the mechanical and thermal properties of the crust are questions that remain under active investigation. Some calculations suggest that the pasta layer may be the strongest material in the universe, more resistant to deformation than any other known substance. If these predictions are correct, then somewhere beneath the surface of every neutron star, there exists a layer of matter arranged in shapes resembling Italian cuisine, a thought that carries a quiet humor, a reminder that even at the extremes of physics, human pattern recognition finds familiar forms in the unfamiliar. Below the pasta phases, the crust ends. Individual nuclei no longer exist as distinct objects. The boundary between nuclear matter and the surrounding neutron fluid dissolves entirely. We have crossed from the crust into the outer core, a transition that carries us from the realm of exotic but still somewhat recognizable nuclear physics into territory where certainty begins to fade and the deepest questions about matter reveal themselves. The surface and crust of a neutron star, despite their extraordinary nature, represent the parts of these objects that scientists understand with the greatest confidence. The physics of the crust, while extreme, can be modeled using extensions of well-tested nuclear theory. The behavior of electrons, the structure of the lattice, the properties of neutron, rich nuclei, these are areas where theoretical predictions can be checked, at least in part, against laboratory experiments and astronomical observations. But as we move deeper, the connection between theory and experiment grows thinner. The densities increase beyond anything achievable in terrestrial laboratories. The behavior of matter enters regimes where multiple theoretical frameworks compete, and none can be definitively confirmed. The journey inward is also a journey toward the edges of human knowledge, a passage from what we understand toward what we can only hypothesize. The crust has been our introduction. What lies beneath will test the limits of physics itself. Below the crust, the nature of a neutron star changes fundamentally. The lattice of nuclei that gave the crust its rigid structure no longer exists. The pasta phases at the base of the crust have dissolved. Individual nuclei, those increasingly bloated and neutron-rich objects that populated the inner crust, have merged into a continuous fluid. We have entered the outer core, a region that contains the majority of the neutron star's mass, and where matter exists in a state unlike anything found anywhere else in the observable universe. The outer core is composed primarily of neutrons. Roughly 90 to 95% of the particles here are neutrons, with the remainder consisting of protons, electrons, and possibly muons, heavier cousins of the electron, produced when energies are high enough. These particles are not arranged in any crystal structure. They are not locked into lattice positions. They form a continuous, dense quantum fluid, a liquid of subatomic particles packed together at densities equal to, and then exceeding that, found inside an atomic nucleus. To appreciate what this means, consider the density of ordinary nuclear matter inside the nucleus of an atom. Inside the tiny, dense core of even the simplest element, the density is approximately 2.3 times 10 to the 17th kilograms per cubic meter. That number is already staggering. A cubic centimeter of nuclear matter would weigh roughly 230 million metric tons. This is the density of the material that makes up every atomic nucleus in your body, in the earth beneath you, in every star and planet in the universe. But nuclear matter, under normal circumstances, only exists in tiny volumes, the nuclei of individual atoms. each one far smaller than a single atom itself. Inside the outer core of a neutron star, matter exists at nuclear density and above, but not in microscopic nuclei. Instead, this density extends continuously across a region, roughly 15 to 20 kilometers in diameter. The entire outer core is, in a sense, a single enormous nucleus, though one governed by different physics than any nucleus found in a laboratory. The behavior of this nuclear fluid is determined by a set of physical principles that lie at the intersection of quantum mechanics, nuclear physics, and general relativity. Understanding the outer core requires grappling with one of the most challenging problems in modern physics, the nuclear equation of state. The equation of state describes the relationship between the pressure, density, and temperature of a material. For ordinary substances, water, air, iron, the equation of state is well known and can be measured directly in laboratories. For the material inside neutron stars, the equation of state must be calculated from theoretical models of how nuclear particles interact at extreme densities. And this is where the difficulty lies. At the densities found inside an atomic nucleus, the forces between protons and neutrons, collectively known as nucleons, are governed by the strong nuclear force, one of the four fundamental forces of nature. The strong force is immensely powerful at short range, far stronger than gravity or electromagnetism. It is what holds atomic nuclei together against the electromagnetic repulsion between positively charged protons. But the strong force is also extraordinarily complex. Unlike gravity or electromagnetism, which follow relatively simple mathematical descriptions, the strong force between nucleons involves intricate interactions that depend on distance, orientation, spin, and the quantum states of the particles involved. At the densities found in ordinary nuclei, these interactions are reasonably well understood. Decades of experimental nuclear physics have provided detailed measurements of how nucleons behave at normal nuclear density. But inside the outer core of a neutron star, densities can reach 2, 3, 4, or even more times nuclear saturation density. At these elevated densities, the distances between nucleons shrink, and the character of the strong force interactions may change in ways that are not fully constrained by laboratory experiments. Different theoretical models predict different behaviors, different pressures, different compositions, different structures. This uncertainty is not a minor technical detail. The equation of state determines essentially everything about the macroscopic properties of a neutron star. It determines the maximum mass a neutron star can achieve before collapsing into a black hole. It determines the radius of a neutron star of a given mass. It determines how much the neutron star deforms under tidal forces, a quantity that becomes measurable when two neutron stars spiral toward each other and merge. It determines the thickness of the crust, the density at the core, and the speed of sound through the stellar interior. Constraining the equation of state is, in many ways, the central problem of neutron star physics, and, for decades, progress was painfully slow. Theoretical models proliferated, each one producing a different equation of state, each one leading to different predictions for the structure and behavior of neutron stars. Without sufficient observational data to distinguish between them, physicists were left with a landscape of possibilities rather than a single clear answer. That began to change in the second decade of the 21st century, when new observational tools provided the first strong constraints on the equation of state. We will return to those observations later in this documentary. For now, it is enough to understand the challenge, to appreciate that the material composing the outer core of a neutron star represents a regime of physics where fundamental uncertainties persist and where the answers carry implications far beyond astrophysics. Within this nuclear fluid, several remarkable phenomena are believed to occur. The neutrons in the outer core like those in the inner crust, are predicted to form a superfluid. In this state, the neutron fluid flows without viscosity, without any internal friction or resistance to flow. The superfluid state arises because neutrons, at sufficiently low temperatures relative to the relevant nuclear energy scales, form pairs known as Cooper pairs, named after the physicist Leon Cooper, whose work on electron pairing helped explain superconductivity in metals. When neutrons pair in this way, they behave collectively as bosons particles that can occupy the same quantum state, and the entire fluid transitions into a coherent quantum state that flows without dissipation. The protons in the outer core are predicted to undergo a similar pairing process. But because protons carry electric charge, their paired state has an additional consequence. Paired protons do not merely flow without viscosity, they conduct electricity without resistance. The proton component of the outer core is predicted to be a superconductor. A superconducting fluid has a distinctive relationship with magnetic fields. In an ordinary superconductor, magnetic fields are expelled from the interior, a phenomenon known as the Meissner effect, observed in laboratory superconductors and responsible for the dramatic demonstrations of magnetically levitated objects floating above superconducting materials. But inside a neutron star, the magnetic field is already present and extremely strong, having been compressed and amplified during the stellar collapse that formed the neutron star in the first place. The interaction between the superconducting proton fluid and the pre-existing magnetic field creates complex structures, quantized magnetic flux tubes, that thread through the superconducting region, each one carrying a precisely defined quantity of magnetic flux. These flux tubes are not mere theoretical curiosities. Their behavior affects the evolution of the neutron star's magnetic field over time. As the neutron star spins down and its rotation changes, the flux tubes may interact with the superfluid neutron vortices, quantized whirlpools, in the neutron superfluid that carry the star's angular momentum. The interplay between these two types of quantized structures, neutron vortices and proton flux tubes, creates a complex internal dynamics that may influence pulsar spin down, magnetic field evolution, and the thermal history of the neutron star. This is physics at its most extraordinary. Inside an object smaller than a city, two interpenetrating quantum fluids, one superfluid and one superconducting, coexist and interact through quantized vortices and flux tubes, all immersed in a sea of electrons, and governed by the strong nuclear force, general relativity, and quantum mechanics simultaneously. No laboratory on Earth can reproduce these conditions. No experiment can directly probe this environment. Everything we know about the outer core comes from theoretical models, constrained by indirect astronomical observations, the timing of pulsar rotations, the spectra of X-ray emissions, the cooling rates of young neutron stars, and more recently, the gravitational wave signatures of neutron star mergers. The outer core is also where the question of composition becomes increasingly uncertain. At densities near and slightly above nuclear saturation, the composition is relatively well understood: neutrons, protons, electrons, and possibly muons. But as density increases deeper into the core, new particles may begin to appear. One possibility involves hyperons, particles similar to protons and neutrons, but containing one or more strange quarks. Under normal conditions, hyperons are unstable and decay rapidly. But at the extreme densities found in neutron star cores, the energy required to create hyperons may become favorable, and they could appear as a stable component of the nuclear fluid. The presence of hyperons would soften the equation of state, reducing the pressure at a given density and potentially lower the maximum mass that a neutron star could support. This creates a theoretical problem. Observations have identified neutron stars with masses approaching and exceeding 2 solar masses. Many equations of state that include hyperons predict maximum masses below this value, meaning that if hyperons do appear, some other mechanism must provide additional pressure to support these massive neutron stars. This tension between the predicted appearance of hyperons and the observed high masses of some neutron stars is known as the hyperon puzzle, and it remains one of the unresolved challenges in neutron star physics. The outer core, then, is not simply a uniform ball of neutrons. It is a layered, complex, quantum mechanical environment where multiple particle species may coexist, where superfluidity and superconductivity may operate simultaneously, and where the fundamental physics governing the behavior of matter remains incompletely understood. It is a region where the known and the unknown exist side by side, where decades of theoretical work have produced detailed predictions that await further observational confirmation. And yet, for all its complexity, the outer core is not the most mysterious part of a neutron star. As density continues to increase toward the very center of the star, we approach a boundary beyond which even the theoretical models begin to diverge dramatically. Below the outer core lies the inner core, a region where matter may take forms that have never been observed, never been measured, and never been recreated in any experiment. The outer core has tested our understanding. The inner core will take us beyond it. At the very center of a neutron star, in a region perhaps only a few kilometers across, matter reaches densities that may exceed 5, 6, or even 10 times the density found inside an ordinary atomic nucleus. No particle accelerator on Earth has ever sustained matter at these densities. No theoretical framework has been definitively confirmed at these extremes, and no observation has yet provided a clear, unambiguous window into what exists in this innermost region. This is the inner core, the heart of the neutron star, and the deepest mystery in the physics of dense matter. To understand why the inner core remains so uncertain, it helps to recall what matter is made of at its most fundamental level: protons and neutrons, the nucleons, that make up every atomic nucleus, and the primary constituents of the outer core are not themselves elementary particles. They are composite objects. Each proton and each neutron is composed of 3 smaller particles called quarks, bound together by the strong nuclear force, which is mediated by particles called gluons. In a proton, 2 up quarks and 1 down quark are held together by a continuous exchange of gluons. In a neutron, 2 down quarks and 1 up quark are bound in the same way. Under normal conditions, inside ordinary atomic nuclei, inside the outer core of a neutron star, these quarks are permanently confined within their parent nucleons. They do not escape. They do not exist independently. The strong force, paradoxically, grows stronger as quarks are pulled apart, ensuring that isolated quarks are never observed under ordinary circumstances. This property is known as confinement, and it is one of the most fundamental features of the strong nuclear force as described by the theory of quantum chromodynamics. But confinement may not be absolute. Theoretical calculations suggest that at sufficiently high densities or temperatures, the boundaries between individual nucleons could dissolve. The quarks that were previously confined within protons and neutrons might begin to move freely across a larger volume, no longer bound to any specific nucleon. The matter would transition from a collection of distinct nucleons into a continuous fluid of quarks and gluons, a state known as quark matter. This transition, sometimes called deconfinement, has been predicted by quantum chromodynamics for decades. At extremely high temperatures, it is expected to occur, and there is experimental evidence from heavy ion collision experiments at facilities like the Relativistic Heavy Ion Collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN, that a quark-gluon plasma was indeed produced in the earliest moments after collisions between gold or lead nuclei at near light speed. These experiments create tiny, unimaginably hot fireballs lasting for only the briefest fractions of a second, conditions thought to resemble the state of the universe microseconds after the Big Bang. But the conditions inside a neutron star core are fundamentally different. The temperatures, while high by everyday standards, are low compared to the energies involved in heavy ion collisions. The densities, however, are far higher and sustained indefinitely. Whether quark matter appears under these conditions cold, extraordinarily dense, and in equilibrium is a question that theory alone has not been able to answer definitively. If quark matter does exist inside neutron star cores, it would represent one of the most extraordinary states of matter in the universe. The quarks would not simply float freely like molecules in a gas. At the extreme densities of the inner core, theoretical models predict that quarks would interact strongly with one another, forming new types of paired states. Just as neutrons in the outer core may form Cooper pairs and become superfluid, quarks in a deconfined state may form their own Cooper pairs, but with a richer and more complex structure, because quarks come in 3 varieties of a quantum property called color charge, and 2 varieties of the relevant quark flavors at these densities, namely up and down, with the possible addition of strange quarks. The resulting state is known as color superconductivity, and it represents some of the most exotic physics predicted anywhere in nature. In the most symmetric version, known as color flavor-locking quarks, of all available, colors and flavors pair together in a pattern that simultaneously breaks the symmetries of both the strong force and the electromagnetic force. The resulting material has properties unlike anything in ordinary experience. It is simultaneously a superconductor, a superfluid, and a medium in which the fundamental forces of nature manifest in altered ways. Whether color superconducting quark matter actually exists inside neutron stars is unknown. The theoretical calculations are extraordinarily difficult, involving approximations and assumptions whose validity at relevant densities remains uncertain. Different approaches yield different predictions for the critical density at which deconfinement occurs, the nature of the transition, and the properties of the resulting quark matter phase. There is another possibility, one that has fascinated and troubled physicists in equal measure since it was first seriously proposed in the 1980s. It involves a particular type of quark matter known as strange quark matter. Under normal conditions, matter is composed of up and down quarks, the 2 lightest varieties. Strange quarks, the next heaviest, are produced in high-energy collisions, but decay rapidly back into lighter quarks. They do not persist in ordinary matter. However, in 1984, the physicist Edward Witten proposed a remarkable hypothesis. He suggested that matter composed of roughly equal numbers of up, down, and strange quarks might actually be more stable than ordinary nuclear matter. That strange quark matter might represent the true ground state of matter, the lowest energy configuration possible. If this hypothesis is correct, and it remains unproven, the implications would be extraordinary. It would mean that every atomic nucleus in the universe is technically metastable, persisting only because the energy barrier to conversion into strange quark matter is prohibitively high under normal conditions. But inside a neutron star, where densities are already at nuclear levels and above, this barrier might be overcome. The conversion of neutron star matter to strange quark matter could, in principle, propagate outward from the core, transforming the entire neutron star into a strange star, an object composed entirely of strange quark matter, held together not by gravity alone, but by the strong force itself. Strange stars, if they exist, would look remarkably similar to ordinary neutron stars from the outside. They would have comparable masses and radii. They would spin rapidly. They would possess strong magnetic fields. Distinguishing a strange star from a conventional neutron star using current observational techniques is extremely challenging, which is precisely why the hypothesis remains neither confirmed nor refuted. The strange matter hypothesis also raises a more unsettling question. If strange quark matter is truly the ground state of matter, then small lumps of it called strangelets could theoretically exist as stable objects. A strangelet encountering ordinary matter might convert that matter into strange quark matter, growing in the process. This possibility has been discussed in the context of heavy ion collisions and cosmic ray interactions, though calculations suggest that the conditions necessary to form stable strangelets are extremely unlikely to be met in any terrestrial experiment. The concern remains theoretical, and no evidence for strangelets has ever been found. Between the known physics of the outer core and the speculative possibilities of the deepest interior, there may exist yet another possibility, a mixed phase, in which regions of quark matter and regions of nuclear matter coexist side by side. This mixed phase could take the form of droplets, rods, or sheets of one phase embedded within the other, not entirely unlike the nuclear pasta structures predicted at the base of the crust. The geometry of the mixed phase, if it exists, would depend on the surface tension between quark matter and nuclear matter, a quantity that is poorly constrained by current theory. The inner core, then, is not a single well-defined entity. It is a space of possibilities, a region where the behavior of matter is determined by physics that remains at the frontier of human understanding. It might be composed of hyperons, exotic baryons containing strange quarks, but still confined within nucleon-like structures. It might contain a mixed phase of nuclear and quark matter. It might be entirely composed of deconfined quark matter, possibly in a color superconducting state, or it might contain strange quark matter, representing the ultimate ground state of all matter in the universe. Each of these possibilities leads to a different equation of state, a different relationship between pressure and density, and different predictions for the observable properties of neutron stars. The challenge of modern neutron star physics is to find ways to distinguish between these possibilities, using the indirect evidence available, the masses and radii of neutron stars, their cooling rates, their spin behavior, their response to tidal forces, and the gravitational wave signals they produce when they collide. It is a remarkable scientific situation. The answers to some of the most fundamental questions about the nature of matter may be encoded in the interiors of objects. Thousands of light years away, objects too small to image directly, too dense to recreate in any laboratory, and too extreme for any single theoretical framework to describe with complete confidence. The inner core of a neutron star is not simply a place. It is a question, perhaps one of the deepest, that physics has ever asked. What is matter? Truly, when everything familiar about it has been stripped away, when atoms no longer exist, when nucleons may no longer hold together, when the very quarks that compose our world may rearrange into configurations never before encountered. The answer, if it comes, will not emerge from any single observation or any single calculation. It will emerge from the slow, painstaking convergence of theory and observation as each new measurement narrows the space of possibilities and brings us incrementally closer to understanding what exists at the densest points in the cosmos. For now, the inner core keeps its secrets, but as we will see, the universe has recently provided new tools that allow us to probe these depths in ways that would have been unimaginable only a few decades ago. For most of the history of neutron star research, scientists faced a fundamental limitation. They could observe the outsides of these objects, their rotation, their magnetic emissions, their surface temperatures, but the interiors remained hidden behind impenetrable barriers of gravity and density. Theoretical models multiplied, each proposing a different equation of state, a different internal composition, a different answer to the question of what lies at the center. But without observational constraints powerful enough to distinguish between competing theories, the interior of the neutron star remained, in many ways, a matter of educated speculation. That era began to end on August 17, 2017. On that date, the Laser Interferometer Gravitational Wave Observatory, LIGO, and the European Virgo detector simultaneously recorded a gravitational wave signal, unlike any they had detected before. Previous detections, beginning with the historic first observation in September 2015, had all involved the mergers of binary black holes, pairs of black holes spiraling inward and colliding in events that produce gravitational waves but no electromagnetic radiation. Black hole mergers are dark. They produce ripples in space-time, but they leave no visible afterglow, no light for conventional telescopes to observe. The signal detected on August 17, 2017 was different. Designated GW170817, it lasted far longer than the black hole merger signals, roughly 100 seconds of observable gravitational wave emission, compared to fractions of a second for the final moments of black hole collisions. The waveform was consistent, not with merging black holes, but with two neutron stars, spiraling inward toward each other, orbiting faster and faster, drawing closer with each revolution until they finally collided. Less than 2 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope detected a short burst of gamma rays from the same region of the sky. Within hours, telescopes around the world turned toward a galaxy called GC 4993, roughly 130 million light-years away in the constellation Hydra. There, in the outskirts of an ordinary elliptical galaxy, they found a new point of light, a transient source that had not been there before, glowing in ultraviolet, optical, and infrared wavelengths. This was the first multi-messenger observation of a neutron star merger. For the first time in history, the same astrophysical event had been detected through both gravitational waves and electromagnetic radiation. The scientific return was extraordinary. Dozens of observatories across the electromagnetic spectrum contributed to the follow-up campaign, producing one of the most intensively studied astrophysical events in recorded history. But among the many scientific results that emerged from GGW 1708 ES17, one category was particularly relevant to the question at the heart of this documentary: the gravitational wave signal itself, the precise shape of the waveform recorded by LIGO and Virgo during the final orbits before collision contained information about the internal structure of the two neutron stars. As two neutron stars orbit each other in the final stages before merger, the gravitational field of each star raises tides on the other. These tidal effects are not unlike the tides that the Moon raises on Earth's oceans, though the scale and intensity are incomparably greater. The degree to which a neutron star deforms under the tidal influence of its companion depends on how compressible its interior is. In other words, on the equation of state, a neutron star with a stiff equation of state, one that resists compression strongly, would be larger for a given mass and would deform more under tidal forces. A neutron star with a soft equation of state would be smaller and more compact, deforming less. This tidal deformation leaves a measurable imprint on the gravitational wave signal. By carefully analyzing the waveform of GGW 170817, scientists were able to extract a quantity called the tidal deformability, a direct measure of how much the neutron stars were distorted during their final orbits. This measurement, while subject to uncertainties, provided the first gravitational wave constraint on the equation of state of dense matter. The results were significant. The tidal deformability, measured from GW 170817, disfavored the stiffest equations of state, those that predicted very large neutron star radii and highly deformable interiors. At the same time, the observation of neutron stars with masses around 2 solar masses, confirmed through earlier radio pulsar measurements, ruled out the softest equations of state, those that could not support such massive objects against gravitational collapse. Together, these constraints began to narrow the range of physically plausible equations of state, squeezing the theoretical possibilities from both sides. For the first time, the interior of a neutron star was being probed not through theoretical calculation alone, but through direct measurement of how these objects respond to the most extreme gravitational environment in the universe. The electromagnetic observations of GW 17081 provided additional insights. The optical and infrared afterglow of the merger, a phenomenon called a kilonova, was powered by the radioactive decay of heavy elements synthesized in the collision. For decades, astrophysicists had suspected that neutron star mergers might be a primary site for the production of heavy elements through a process called rapid neutron capture, or the R process. The observations of the kilonova associated with GW 17081 provided strong evidence that this was indeed the case. The spectral signatures were consistent with the production of elements including gold, platinum, and uranium elements whose cosmic origins had been debated for years. This discovery carried a quiet poetry that no documentary can ignore. The gold in a wedding ring, the platinum in a laboratory instrument, the uranium that powers certain reactors, these elements, forged in the violent collision of 2 neutron stars, were scattered into space and eventually incorporated into the clouds of gas that formed new stars and planetary systems, including our own. Every atom of gold on Earth was likely created in such an event billions of years before our solar system existed, while GW 17081 provided the first gravitational wave constraints on neutron star interiors. Another observational program was approaching the problem from a different direction by measuring the sizes of neutron stars directly. In June 2017, just 2 months before the neutron star merger detection, NASA installed an instrument on the International Space Station called the Neutron Star Interior Composition Explorer, NISA. The name was deliberate. NISA was designed specifically to measure the radii of neutron stars by observing the X-ray emission from their surfaces with extraordinary precision. The principle behind NISA's measurements is conceptually elegant, though technically demanding. A neutron star's surface emits thermal X-rays. As these X-rays travel outward through the intense gravitational field surrounding the neutron star, their paths are bent by general relativity. The degree of bending depends on the compactness of the neutron star, the ratio of its mass to its radius. A more compact neutron star bends light more strongly, causing a larger fraction of its surface to be visible to a distant observer at any given time. By carefully modeling the observed X-ray pulse profiles of rotating neutron stars, the way the X-ray brightness varies as the star spins and hotspots on its surface rotate in and out of view, NISA can simultaneously constrain both the mass and the radius. The initial results from NISA, published beginning in 2019, focused on a millisecond pulsar known as PSR J0030+0451. Millisecond pulsars are neutron stars that have been spun up to extremely rapid rotation rates through the accretion of matter from a companion star. PSR J0030+0451 rotates approximately 205 times per second, and NISA observed it for an extended period, accumulating enough X-ray photons to perform a detailed analysis of its pulse profile. The results indicated a radius of approximately 12 to 13 kilometers for a neutron star of roughly 1.4 solar masses. Subsequent NISA analyses of other neutron stars, including the more massive PSR J0740+6620, which has a mass of approximately 2 solar masses, yielded similar radius estimates. These measurements were remarkable for what they implied. that neutron stars of very different masses have surprisingly similar radii. This finding favors equations of state that are moderately stiff, producing neutron stars that are neither very large nor very small, and that do not compress dramatically as mass increases. Combined with the tidal deformability measurement from GW170811, the NICER radius measurements have significantly constrained the equation of state. The range of plausible models has narrowed considerably compared to even a decade ago. While the exact composition of the core remains undetermined, the macroscopic properties of neutron stars, their sizes, their deformabilities, their maximum masses, are becoming increasingly well measured. These observational advances have not resolved the fundamental question of whether quark matter, strange matter, or purely nucleonic matter exists at the highest densities, but they have changed the character of the problem. What was once a landscape of almost unconstrained theoretical possibilities has become a much more focused investigation, guided by real measurements and bounded by observational limits. Additional gravitational wave detections of neutron star mergers, expected as LIGO, Virgo, and the Japanese Kagra detector, continue to improve in sensitivity, will provide further constraints. Each new detection offers an independent measurement of tidal deformability, and the accumulation of multiple measurements will progressively tighten the observational bounds on the equation of state. Future X-ray observatories, with greater collecting area and improved energy resolution, may refine radius measurements further. And proposed next-generation gravitational wave detectors, such as the Einstein telescope in Europe and Cosmic Explorer in the United States, could detect neutron star mergers at far greater distances and with far greater precision, opening an era of precision neutron star physics. The story of neutron star observation is, in many ways, a story about patience. For decades after their discovery, neutron stars were studied primarily through their radio emissions, the lighthouse beams of pulsars sweeping across Earth. Then came X-ray astronomy, opening a new window on neutron star surfaces and accretion processes. Then came gravitational wave astronomy, providing a direct probe of the bulk properties of neutron star matter. Each new observational channel has revealed something that the previous ones could not, and each has brought scientists closer to understanding what lies inside. The convergence of these observational methods, radio timing, X-ray spectroscopy, gravitational wave analysis, represents one of the most powerful approaches in modern astrophysics. No single method can answer the question alone, but together, they are gradually assembling a coherent picture of neutron star interiors, constraining the equation of state from multiple independent directions and narrowing the space of possibilities that theory must explore. The inner core may still hold its secrets, but the tools to uncover them are now in hand. And with each passing year, each new observation, each refined measurement, the boundary between what we know and what we do not know shifts inward toward the center, toward the answer. Not all neutron stars are alike. While every neutron star shares the same basic origin, the collapsed core of a massive star, the conditions of their birth and their subsequent evolutions can produce objects with remarkably different properties. Understanding these differences has become one of the most productive avenues for studying the physics of ultra-dense matter, because each type of neutron star reveals something different about the interior. The most familiar type, and the first to be discovered, is the rotation-powered pulsar, the kind of object Jocelyn Bell detected in 1967. These neutron stars emit beams of radio waves, powered by the energy of their rotation. As they spin down over millions of years, losing rotational energy through electromagnetic radiation, their pulse periods gradually lengthen. Most known pulsars fall into this category, and their extraordinary rotational stability has made them some of the most precise clocks in the universe. A distinct subclass within this category is the millisecond pulsar, a neutron star spinning hundreds of times per second. Millisecond pulsars are believed to be old neutron stars that have been recycled, spun back up to rapid rotation through the accretion of matter from a close binary companion. As material spirals onto the neutron star from the companion, it transfers angular momentum, gradually increasing the spin rate over millions of years. The result is a neutron star rotating at speeds that seem almost impossible, the surface at the equator moving at a significant fraction of the speed of light. Millisecond pulsars are particularly valuable for probing neutron star interiors because their rapid rotation places constraints on the equation of state. A neutron star spinning at several hundred rotations per second must be compact enough and structurally strong enough to resist being torn apart by centrifugal forces. If the equation of state were too soft, if the neutron star were too large for its mass, it would not survive at such rotation rates. The mere existence of millisecond pulsars rules out certain equations of state and constrains the compactness of these objects. But there is another class of neutron star that has dramatically expanded our understanding of the extremes these objects can reach. They are among the most magnetically powerful objects in the known universe, and their discovery opened an entirely new chapter in neutron star physics. They are called magnetars. The magnetic field of an ordinary neutron star is already extraordinary by any terrestrial standard. A typical pulsar might have a surface magnetic field on the order of 100 million Tesla, roughly 1 trillion times stronger than the magnetic field at Earth's surface. This alone is difficult to comprehend. The strongest sustained magnetic fields ever produced in laboratories on Earth reach only a few tens of Tesla. The magnetic field of a refrigerator magnet is roughly 5,000ths of a Tesla. The gap between human-generated magnetic fields and those of ordinary pulsars is staggering. Magnetars exist on an entirely different scale. A magnetar's surface magnetic field may reach 10 billion Tesla, or more, roughly 1,000 times stronger than that of a typical pulsar, and 100 trillion times stronger than the strongest laboratory magnets. At these field strengths, the magnetic field fundamentally alters the behavior of matter and radiation. The energy stored in a magnetar's magnetic field is immense, comparable to the total energy output of the sun over an extended period. The effects of such extreme magnetic fields are profound and, in many cases, deeply counterintuitive. At field strengths approaching those found on magnetar surfaces, the vacuum of empty space itself is predicted to become birefringent, meaning it would bend light differently depending on its polarization, much as certain crystals split a single beam of light into two. This effect, predicted by quantum electrodynamics, has never been directly confirmed in laboratory experiments because the required field strengths are far beyond human capability. But around magnetars, the conditions for vacuum birefringence may be routinely met. At the surface of a magnetar, the magnetic field also reshapes atomic structure. Atoms in a strong magnetic field become elongated along the field lines, their electron orbitals stretched into long, thin cylinders rather than the familiar spherical shells. Chemistry, in any recognizable sense, ceases to function. The ordinary rules governing how atoms bond and interact, the rules that underpin all of terrestrial chemistry and biology, break down entirely. Matter at a magnetar's surface exists in a state with no analog anywhere on Earth. Magnetars were first identified through their observational behavior, specifically through two types of energetic phenomena that could not be explained by ordinary pulsars. The first type is the soft gamma repeater, or SGR. Soft gamma repeaters are sources that emit repeated bursts of gamma rays and hard X-rays, with energies far exceeding anything that rotational energy alone could produce. These bursts are irregular, sometimes occurring in clusters, and sometimes separated by long periods of quiet. The most dramatic example occurred on December 27, 2004, when the magnetar SGR 180620 produced a giant flare so intense that it momentarily affected Earth's ionosphere from a distance of roughly 50,000 light-years. For a fraction of a second, this single neutron star, smaller than a city, released more energy than the Sun emits in hundreds of thousands of years. The second type is the anomalous X-ray pulsar, or AXP. These are neutron stars that emit persistent X-rays at luminosities too high to be explained by their rotational energy loss. Unlike ordinary pulsars, whose emission is powered by spin down, the X-ray emission from AXPs appears to be powered by the decay of their extreme magnetic fields. The magnetic energy stored within the neutron star is gradually dissipated, heating the interior and surface and producing the observed persistent X-ray emission along with occasional bursts. Today, soft gamma repeaters and anomalous X-ray pulsars are understood as manifestations of the same underlying phenomenon neutron stars. With ultra-strong magnetic fields, the unified magnetar model, developed primarily by the astrophysicists Robert Duncan and Christopher Thompson in the early 1990s, explains both the persistent emission and the bursting behavior as consequences of the enormous magnetic energy stored within and around these objects. The origin of magnetar strength magnetic fields is itself a subject of active research. The leading theory suggests that magnetars are born in supernova explosions where the collapsing core experiences rapid differential rotation and vigorous convection during the first seconds after collapse. These conditions could amplify an initial magnetic field through a dynamo process, the same general mechanism that generates magnetic fields inside Earth and the Sun, but operating at incomparably greater intensities and speeds. If the conditions are right, the magnetic field could be amplified to magnetar strength levels within the first 30 seconds of the neutron star's existence, then frozen into the stellar structure as the interior settles. For the question of neutron star interiors, magnetars provide unique diagnostic value. The extreme magnetic fields penetrate deep into the neutron star, threading through the crust, the outer core, and potentially into the inner core. The behavior of the magnetic field, how it evolves over time, how it interacts with the superfluid and superconducting components of the interior, how it stores and releases energy, depends on the physical properties of the matter it passes through. By studying the timing behavior, burst activity, and spectral properties of magnetars, scientists can gain indirect information about the conditions deep inside. One particularly informative window into neutron star interiors comes not from magnetic activity, but from something far quieter: the slow, gradual cooling of neutron stars over time. When a neutron star is first born in a supernova explosion, its interior temperature may exceed 100 billion degrees. At these temperatures, the neutron star is a prolific emitter of neutrinos, nearly massless particles that interact only weakly with matter and can escape from the neutron star's interior almost freely. In the first minutes and hours after formation, neutrino emission is the dominant cooling mechanism, carrying away energy far more efficiently than surface photon emission. Over the following years, decades, centuries, and millennia, the neutron star gradually cools. The rate at which it cools depends critically on the processes occurring in its interior, and different compositions and states of matter cool at different rates. This makes neutron star cooling a potentially powerful diagnostic tool for constraining the interior composition. The physics behind this connection is subtle but profound. In a neutron star composed purely of neutrons, protons, and electrons, the dominant neutrino emission process at moderate temperatures is called the modified Urca process, a relatively slow reaction chain in which neutrons and protons convert into each other while emitting neutrinos and antineutrinos. The modified Urca process produces a gradual, steady cooling rate. However, if the proton fraction in the core exceeds a critical threshold, typically estimated at around 11 to 15% of the total baryon number, a faster process becomes possible. This is the direct Urca process, in which a neutron decays into a proton, electron, and antineutrino, followed by the reverse reaction, in which a proton captures an electron to produce a neutron and a neutrino. The direct Urca process is far more efficient than the modified version, and if it operates, the neutron star cools dramatically faster. The critical proton fraction required for the direct Urca process depends on the equation of state. Stiffer equations of state generally predict higher proton fractions at a given density, making the direct Urca process more likely to operate. Thus, the observed cooling rates of neutron stars can, in principle, constrain the equation of state, providing yet another observational handle on the interior composition. If exotic particles are present in the core hyperons, free quarks, or other non-standard components, additional neutrino emission channels may become available, potentially accelerating cooling even further. The presence of superfluidity also affects cooling, as the formation of Cooper pairs releases neutrinos while simultaneously suppressing certain emission processes by creating an energy gap that particles must overcome to participate in reactions. The interplay between these processes creates a complex cooling landscape. Different assumptions about the interior composition, the equation of state, the presence or absence of superfluidity, and the onset of exotic matter all produce different cooling curves predictions of how the surface temperature of a neutron star should decline over time. Comparing these predicted cooling curves with observed temperatures of neutron stars at known ages provides one of the most direct tests of interior models. Several neutron stars have measured surface temperatures and reasonably well-determined ages, either from historical supernova records or from the measured expansion rates of their surrounding remnant nebulae. The neutron star in the Cassiopeia, a supernova remnant, for example, has been studied intensively. Born in a supernova explosion estimated to have occurred around 1680, this roughly 300-year-old neutron star has been observed to cool over a period of years by space-based X-ray telescopes. Some analyses have suggested that the observed cooling rate is consistent with the recent onset of neutron superfluidity in the core, a transition that would temporarily enhance neutrino emission as Cooper pairs form, producing a brief period of accelerated cooling before the superfluid energy gap suppresses further emission. This interpretation remains debated, and the observational uncertainties are significant, but the possibility that we might be directly observing the formation of a superfluid state inside a neutron star, watching a quantum phase transition unfold in real time inside an object 300 light-years away, represents one of the most remarkable intersections of observation and fundamental physics in modern astrophysics. The diversity of neutron star phenomena, pulsars, millisecond pulsars, magnetars, cooling neutron stars, accreting neutron stars in binary systems provides a rich observational landscape. Each type of neutron star offers a different perspective on the interior, probing different density regimes, different temperature ranges, different magnetic environments. No single type of neutron star can answer the question of what lies inside on its own, but taken together, they form a web of constraints that progressively narrows the range of possible interior models. It is this convergence, the combination of gravitational wave measurements, X-ray observations, radio timing, cooling curves, and the study of extreme magnetic phenomena that gives modern neutron star physics its power. The question of what lies inside a neutron star is not being answered by any single breakthrough it is being answered by the slow accumulation of evidence from multiple independent sources, each one confirming, refining, or ruling out theoretical predictions. The inner core may still be hidden from direct view, but the neutron stars themselves, in their extraordinary variety, are speaking. And with each passing year, we are learning to listen more carefully. Every neutron star exists in a state of tension, a balance between forces so extreme that even a small shift in either direction would transform the object entirely. On one side is gravity, pulling inward with relentless force, attempting to compress the star further. On the other side is the pressure of ultra-dense matter-neutron degeneracy pressure, nuclear repulsion, and whatever additional forces the equation of state provides pushing outward, resisting further collapse. This balance defines the neutron star. It determines its size, its density, its structure, and ultimately, its fate. And this balance has a limit. There is a maximum mass that any neutron star can achieve. Beyond that threshold, no known force in the universe can prevent the star from collapsing, entirely falling inward past the point of no return and forming a black hole. This maximum mass is known as the Tolman-Oppenheimer-Volkoff limit, named after the three physicists who first calculated it in 1939, Richard Tolman, J. Robert Oppenheimer, and George Volkoff. Their work, published just 5 years after Bardet and Zwicky first proposed the existence of neutron stars, established the theoretical framework for understanding stellar objects held in equilibrium by the pressure of degenerate matter under the conditions of general relativity. The precise value of the Tolman-Oppenheimer-Volkoff limit depends on the equation of state, on the relationship between pressure and density inside the neutron star. A stiffer equation of state, one that provides greater pressure at a given density, supports a higher maximum mass. A softer equation of state yields a lower maximum mass. Because the equation of state remains incompletely determined, the exact value of the maximum mass is not precisely known. Current estimates, informed by both theoretical models and observational constraints, suggest it lies somewhere between approximately 2.1 and 2.5 solar masses, though the boundaries of this range continue to be refined. The observational determination of neutron star masses has been one of the most important contributions to this problem. The most precise mass measurements come from binary pulsar systems, neutron stars in orbit with another star, where the orbital dynamics allow accurate mass determination through the techniques of pulsar timing. One of the most significant measurements was published in 2010 when a team of astronomers used the Green Bank telescope in West Virginia to measure the mass of PSR J Winck's 1-Fall 2230, a millisecond pulsar in a binary system with a white dwarf companion, by detecting a relativistic effect known as Shapiro delay, the time delay experienced by the pulsar's radio signals as they pass through the curved space-time near the companion star. The team determined the pulsar's mass to be approximately 1.97 solar masses. This single measurement had a profound impact on neutron star physics because it immediately ruled out all equations of state that could not support a neutron star of nearly 2 solar masses. Subsequent measurements pushed the boundary further. PSR J 348 plus 432, measured in 2013, yielded a mass of approximately 2.01 solar masses, and PSR J 07406620, measured in 2019 through a similar Shapiro delay technique, produced a mass of approximately 2.08 solar masses, the highest precisely measured neutron star mass at that time. Each new high mass measurement eliminates additional equations of state from the lower end of the theoretical landscape, constraining the properties of matter at the highest densities. These measurements have been particularly consequential for the hyperon puzzle discussed earlier. Many equations of state that include hyperons' strange quark containing baryons predicted to appear at high densities, produce maximum masses below 2 solar masses. The confirmed existence of neutron stars at or above this threshold means that either hyperons do not appear as predicted, or some additional repulsive mechanism exists at high densities that compensates for the softening effect of hyperons. Resolving this tension requires either new theoretical insights into the strong force at high densities or new observational data that can more precisely constrain the composition. The maximum mass question also connects directly to one of the most dramatic events in astrophysics, the formation of black holes from neutron star collapse. When a neutron star in a binary system accretes enough material from its companion to exceed the maximum mass, or when 2 neutron stars merge and the combined remnant exceeds the limit, the result is gravitational collapse. The matter that was held in equilibrium by nuclear pressure falls inward, forming a black hole, an object whose interior is shielded from the outside universe by an event horizon. The merger of 2 neutron stars, as observed in the GW 170817 event, provides a natural laboratory for studying this boundary. When 2 neutron stars collide, the immediate aftermath depends critically on the total mass of the system and the equation of state. If the combined mass is below the maximum mass, the merger may produce a stable neutron star, a rare outcome thought to occur only for relatively low mass binaries. If the combined mass is above the maximum mass, but not by 2, the merger may produce a hypermassive neutron star, an object temporarily supported against collapse by the rapid differential rotation generated during the merger. This hypermassive remnant may survive for milliseconds to seconds before the differential rotation dissipates and the object collapses to a black hole. If the combined mass significantly exceeds the maximum, the collapse to a black hole may occur almost immediately. The fate of the remnant in GW 170817 remains uncertain. The gravitational wave signal ended at the moment of merger, and the post-merger gravitational wave emission, if any, was produced by a briefly surviving remnant, was too weak to be detected by LIGO and Virgo at their sensitivity levels in 2017. The electromagnetic observations provided some indirect constraints, but a definitive determination of whether the remnant briefly survived as a hypermassive neutron star or collapsed promptly to a black hole has not been achieved. Future gravitational wave detectors with improved sensitivity at the high frequencies where post-merger signals are expected may resolve this question for subsequent events. The detection of post-merger gravitational waves from a surviving neutron star remnant would provide extraordinarily direct information about the equation of state at the highest densities reached during the merger densities, potentially exceeding those found in any stable neutron star. Between neutron stars and black holes, there exists a theoretical gap, a range of masses, where neither neutron stars nor black holes have been confidently observed. This gap, roughly between 5 and 5 solar masses, has been called the mass gap. Whether it represents a true absence of objects in this mass range, perhaps because the physics of core collapse supernovae preferentially produces either lighter neutron stars or heavier black holes, or whether objects in this range simply have not yet been detected, remains an open question. Some gravitational wave detections have identified merger components with masses in or near the mass gap, raising the possibility that the gap may be partially populated. Understanding whether these objects are the heaviest possible neutron stars, the lightest possible black holes, or something else entirely is an active area of investigation. The maximum mass question carries significance beyond astrophysics, because the maximum mass depends so sensitively on the equation of state, and because the equation of state depends on the fundamental physics of the strong nuclear force. At high densities, measuring the maximum mass is effectively a measurement of fundamental physics. Each new constraint on the maximum mass is simultaneously a constraint on the behavior of the strong force, on the possible existence of exotic matter, and on the nature of the QCD phase diagram, the map of how matter behaves as a function of temperature and density according to quantum chromodynamics. The boundary between neutron stars and black holes is not merely an astrophysical curiosity. It is a physical threshold, a line drawn by the fundamental forces of nature. Between two qualitatively different fates for matter, on one side of this line, matter achieves a dense but stable equilibrium, creating objects of extraordinary physical richness, superfluid interiors, superconducting cores, crystalline crusts, magnetic fields of unimaginable strength. On the other side, matter collapses beyond the reach of observation, hidden behind an event horizon, its internal state unknown and perhaps unknowable. Where exactly this line falls, what the maximum mass is, what equation of state governs it, what composition of matter determines. The critical pressure remains one of the central questions in modern physics. It is a question that connects the interiors of neutron stars to the most fundamental theories of particle physics and gravity. And it is a question that the current generation of observational tools, gravitational wave detectors, X-ray telescopes, radio timing arrays, is uniquely positioned to answer. The coming decades promise an extraordinary acceleration in our understanding. The LIGO-Virgo-Cagra network continues to improve in sensitivity with each successive observing run. Additional neutron star merger events will provide independent measurements of tidal deformability, each one further constraining the equation of state. NASA continues to accumulate data on neutron star radii, refining its measurements with each additional observation. And the next generation of gravitational wave observatories, currently in the design and planning stages, could detect thousands of neutron star mergers per year, transforming neutron star physics from a data-limited field into a precision science. Radio astronomy, too, continues to advance. New facilities and improved computational techniques are enabling the discovery of more binary pulsar systems, more millisecond pulsars, and more precise mass measurements. The Square Kilometre Array, an international radio telescope project spanning sites in South Africa and Australia, is expected to discover thousands of new pulsars when it reaches its full capability, dramatically expanding the catalogue of known neutron stars and providing mass measurements of unprecedented precision. At the same time, theoretical physics continues to push forward. Advances in computational nuclear physics, including lattice quantum chromodynamics calculations performed on the world's most powerful supercomputers, are beginning to provide first principles constraints on the equation of state at high densities. These calculations are extraordinarily demanding. Solving the equations of quantum chromodynamics on a discrete spacetime lattice requires computational resources at the very frontier of current capability. But they represent the most direct theoretical approach to understanding dense matter from fundamental physics. The convergence of observational capability and theoretical sophistication marks a turning point. For the first time, the question of what lies inside a neutron star is being addressed simultaneously from multiple directions. Gravitational waves from mergers, X-ray observations of surfaces, radio timing of pulsars, cooling curves of young neutron stars, burst observations from magnetars, and first principles theoretical calculations. Each approach provides independent constraints, and together they are assembling a picture of dense matter that is more detailed and more tightly bounded than at any previous point in the history of physics. The answer is not yet complete. The inner core remains elusive. The question of whether quark matter exists in nature is still open. The equation of state, while increasingly constrained, has not been determined to the precision needed to resolve all competing models. But the trajectory is clear. The tools are in place. The observations are accumulating. And the question itself, what is matter? Truly, at the most extreme densities, nature allows is being pursued with a depth and rigor that would have been unimaginable when Bardi and Zwicky first proposed the existence of neutron stars nearly a century ago. The journey toward the center of a neutron star is also a journey toward the limits of physics, and we are closer to those limits than ever before. We began this journey at the surface, a place already more extreme than anything found on Earth, where gravity crushes matter into crystalline structures of extraordinary strength and atoms are stripped to their bare nuclei. We descended through the crust, past lattices of neutron, rich isotopes that exist nowhere else in the universe, through the neutron drip line, where individual nuclei can no longer contain the particles within them, and into the strange geometry of nuclear pasta at the base of the crust matter, twisted into rods, sheets, and tunnels by the competing forces of gravity and nuclear repulsion. We passed into the outer core, where individual nuclei dissolve into a continuous quantum fluid of neutrons, protons, and electrons at nuclear density. We encountered superfluidity and superconductivity quantum mechanical phenomena, operating at scales and temperatures that would seem impossible by the standards of ordinary physics. We explored the intricate dynamics of quantized vortices and magnetic flux tubes, structures that connect the quantum behavior of individual particles to the observable rotation and magnetic evolution of the neutron star as a whole. And we reached the inner core, the place where certainty ends and the deepest questions begin. We considered the possibility that matter at the highest densities may undergo a fundamental transformation, that the quarks confined within protons and neutrons may break free and form entirely new states of matter. We examined the hypothesis that strange quark matter might be the true ground state of all matter in the universe, a proposal that, if correct, would reshape our understanding of the physical world. Along the way, we traced the history of how these objects came to be understood, from the theoretical prediction by Bardi and Zwicky in 1934 through the decades of silence, when neutron stars existed only as mathematical possibilities, to the moment in 1967, when Jocelyn Bell's careful observation of a repeating radio pulse transformed them from theory into observed reality. We followed the story through the identification of pulsars, the discovery of millisecond pulsars and magnetars, and into the modern era of multi-messenger astronomy, an era in which gravitational waves, X-ray telescopes, and radio timing arrays are converging on the same fundamental question from different directions. The question, what lies inside a neutron star, is deceptively simple, a child might ask it. But the answer reaches into the deepest layers of physics, connecting general relativity to quantum mechanics, nuclear physics to particle physics, astrophysics to the most fundamental theories of matter and force. It is a question that, once pursued seriously, leads inevitably to the frontier of human knowledge, to the boundary between what we understand and what we have not yet been able to determine. There is something humbling about this boundary. We have sent spacecraft to the edges of the solar system. We have detected light from galaxies that emitted it more than 13 billion years ago. We have measured the faint ripples in space-time caused by colliding black holes a billion light years away. Our instruments and our theories have carried us to extraordinary distances and extraordinary scales. And yet, inside an object barely 20 kilometers across, smaller than many cities on Earth, there exist conditions that our most powerful theories cannot fully describe. The interior of a neutron star is not merely unexplored, it is, in a very real sense, unexplorable by direct means. No probe can survive the journey. No instrument can withstand the gravitational forces, the pressures, the densities. Everything we know about these interiors must be inferred, pieced together, from the faint signals that escape, from the gravitational waves that ripple outward during collisions, from the X-rays that emerge from surfaces heated by processes occurring kilometers below, from the precise ticking of radio pulses that carry subtle imprints of the quantum mechanical processes operating deep within. This is the nature of the scientific endeavor at its most profound. It is not always about seeing directly. Sometimes it is about listening carefully, measuring precisely, and reasoning honestly from incomplete evidence toward the most faithful picture of reality. That current knowledge allows. The scientists who study two-list neutron stars do not have the luxury of certainty. They work with probabilities, constraints, competing models, and the patient accumulation of evidence. They publish not final answers but refined questions, each one narrower, sharper, and closer to the truth than the one before. And perhaps that is appropriate. The universe does not owe us simplicity. It does not promise that its deepest structures will be easy to understand or quick to reveal. The history of physics is filled with questions that took generations to answer, and some that remain open after centuries of investigation. The nature of matter at extreme density may prove to be one of the great long-duration questions of science, a puzzle that yields its secrets gradually, one observation at a time, one theoretical advance at a time, across decades or longer. But the progress is real. A physicist studying neutron stars in the 1970s could say, with confidence only, that these objects existed, that they were dense, and that they rotated rapidly. The internal structure was almost entirely a matter of theoretical speculation. Today, the equation of state is constrained from multiple independent directions. The radius of a neutron star of known mass has been measured directly. The tidal deformability of merging neutron stars has been extracted from gravitational wave signals. The cooling behavior of young neutron stars has been tracked over years of observation. The theoretical landscape, once vast and nearly unconstrained, has been pruned and focused into a much smaller space of possibilities. We do not yet know whether quark matter exists inside neutron stars. We do not yet know the precise equation of state. We do not yet know whether the inner core contains a color superconducting phase, a hyperonic phase, a mixed phase, or something that has not yet been imagined. But we know far more than we did a decade ago, and we will know far more a decade from now. The trajectory of discovery is unmistakable. In the meantime, the neutron stars themselves continue to exist in their quiet extremity, scattered across the Milky Way, spinning in the darkness, cooling slowly over millennia, occasionally flaring with magnetar bursts, or merging in cataclysmic collisions that scatter heavy elements across space. They are among the most remarkable objects that nature has produced. Each one is a laboratory of fundamental physics, operating continuously under conditions that no human experiment can replicate. There is a thought worth carrying as this documentary draws to a close. The atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you are breathing, were forged in the interiors of massive stars that lived and died long before the sun was born. Some of the heaviest elements in the earth beneath you may have been created in neutron star collisions billions of years ago. The physics that governs the interior of a neutron star is not distant or abstract. It is the same physics that governs the matter that makes up everything you have ever touched or seen. The strong nuclear force that binds quarks into protons and neutrons inside a neutron star core is the same force that holds together every atomic nucleus in your body. The difference is only one of scale, of density, of pressure, of the extremity of conditions. In studying neutron stars, we are studying ourselves, or rather, we are studying the fundamental nature of the matter from which we are made, pushed to conditions where its behavior reveals properties invisible under ordinary circumstances. The interior of a neutron star is a mirror, reflecting back the deepest structures of the physical world in a form that we are only now learning to read. Night after night, the pulsars sweep their beams across the galaxy. Most of those beams will never intersect the Earth. Most of those neutron stars will never be detected by any human instrument. They will spin down over billions of years, cooling imperceptibly, their magnetic fields decaying, their interiors locked away beneath gravity, too strong for light itself to easily escape. They will become dark, cold remnants, dense objects drifting silently through interstellar space, carrying their secrets with them. But some will be found, some will be measured, and from those measurements, slowly, carefully, with the patience that science demands and the curiosity that drives it, we will continue to assemble our understanding of what exists at the densest points in the universe, what matter becomes when everything familiar about it has been stripped away and only the deepest laws of physics remain. The question persists, the search continues, and somewhere in the darkness between the stars, the answer waits compressed into a sphere no wider than a quiet city, spinning in silence, holding within it one of the last great secrets of the physical world.